So in this video, I'd like to continue that understanding of work done by a force on a particle. So we already know that at this point, right, that if we have a particle, the work done on the particle is given by some path, let's say gamma. So you gotta imagine that we have some path in space. Here's your x, here's your y, z, point A, and you're taking gamma path to point B. So we know the work done, right, is equal to the kinetic energy at B minus the kinetic energy at A. So if we want to calculate the work done by a force on a particle that's taking a path gamma, we know that's equal to the kinetic energy of B minus kinetic energy. So this is true for whatever the type of force is. It doesn't matter if the force is a dissipative force or it's a conservative force. So we know that's to be true. But let's take the special case when we know that F is a conservative force. So where do I do? Let's do it over here. So if it's a conservative force, right, I said in lecture, right, that we can write this in terms of the gradient of some potential function dotted with dr, where dr is the position vector. So just to remind you, I'm going to always select the position vector to be r, the radial vector to be xi plus yj plus zk. So this is going to be, and so dr is the displacement of the position vector. So for example, if this is the position vector r, the differential, right, of dr is the displacement going from time t to a time t plus dt. So this is really dxi plus dyj plus dz, where am I? dzk. So this is the differential. So let's expand this integral. So I'm going to do it over here. So here's our gamma path, and we're taking the gradient, so I'll put the minus out, and we get the gradient, which is I, partial of phi with respect to I. Here's j, partial of phi with respect to y, plus k, partial of phi with respect to z. We are dotting it with dxi plus dyj plus dzk. Here's gamma path. Now we expand it in the dot product. So I'm going through these exact details to make sure you understand these details. So we're just applying the dot product. Now this dot product, right? Now if you should look carefully, phi is a function of x, y, and z. And if it is, right, this is the chain rule. So this is the chain rule for multivariable calculus, and we can write this in terms of minus gamma d phi, which is the integral of 1 d phi at the endpoints, right, means that this is the negative of the phi at point B, I'll just say B, minus the potential at point A. And so if we're working with a conservative field, so if F is a conservative field, so we know that F can be written as the negative of gradient of a potential function. And if we do, we get back to phi at B minus phi at A, which in this case happens to be phi at A minus phi at B. The potential at point A, at the endpoints of the path, is phi A, so phi at A minus phi at B. So let me erase this and just summarize the result. And this leads us to an interesting explanation of conservation of energy. So let me erase this. And I'll rewrite it on board over here. So what you're saying is that the work done So there is no concept of conservation of energy until we start introducing the idea of a conservative field. So now if F is a conservative field, the kinetic energy at point B, so remember this is our diagram, here's our curve, here's point B, here's gamma, here's point A, is equal to phi at A minus phi at B. So I'm going to move the A's to one side and the B's to the other, and moving this to the other side, well, this to the other side and phi to the other side, you'll actually see that phi at A plus the kinetic energy at point A is equal to phi at B plus kinetic energy at point B. And this is an important idea. This leads to an idea of concept of conservation of energy. So if we have a particle that's in a conservative field, the work done, so whatever this path is, this is a, so we're saying that irrespective of the path, right, that the energy, we can define energy, the total energy, is equal to something called the potential energy, or the potential function. Potential function plus the kinetic energy is the total energy. But remember, this concept of total energy doesn't really exist until we actually introduced a concept of a conservative function, a conservative field, kinetic energy. So we can define this to be the total energy. This is the total energy before the process and after the process is conserved. And it only works if we can define a potential function, or that the force field is actually a conservative field. So we can actually start working with total energy. So this concept of total energy doesn't make any sense until we start working with conservative fields. And once we do, we actually can have the notion of that total energy is being conserved. I can't spell energy properly, so. And so let me give you an example of this. Let me erase this. So here's an example. So we're told that the potential energy function is equal to, let's make it 3x yz squared. I don't want to really spend time doing like weird complex functions, but whatever this is, we're going to say this is the potential function, or the potential energy if you want. So we know that the force field is the gradient of phi, which I'm not going to calculate because it's just a calculation that we know. It's just a straight substitution. We calculate the partial of x, y, and z. Assuming x, y, and z are independent variables, we can calculate this. I'll leave that alone, dot, 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 not important. And so the question is, the change in the potential energy. So for any path taken from, here's a path, and let's assume this path happens to be the point 1, 1, 1, going to a path 2, 2, 2. So we have any path. It doesn't matter what the path is. Gamma, gamma 1, gamma 2, gamma 3. We know that the total potential energy from point A to point B plus the kinetic energy at point A is equal to the potential energy of B and kinetic energy of B. So it means that if I calculate if I want to know what the change in the kinetic energy is, move to the other side. So the change in the kinetic energy, so move this term KB to the other side, K on the other side, we can say that let me write that down. 0 is equal to phi at B minus phi at A plus kinetic energy at B minus kinetic energy at point A. So what you're saying is the change in the potential energy plus the change in the kinetic energy is equal to 0. So if I want to know what the change in kinetic energy is between those 2 points, I can quickly calculate it to be nothing more than the negative of the change, the delta of phi. So for example, between these 2 points, I can say the kinetic energy change is basically the potential function, which in this case happens to be, well, so this is phi at B minus phi at A. So phi at B is basically 222, so this is 3 times 2 times 2 times 2 squared minus 3 times 1 times 1 times 1 squared. And I won't even bother calculating it. These are small numbers. It's not important. So whatever this is, this answer is, it is equal to the change in kinetic energy. So potential energy, right? The idea of having a potential function, right? And we can get a conservative force from the potential function leads us to a concept of conservation of energy. So for a single particle, later I'll actually show you that systems of particles using the third law, right? Newton's third law, and systems of particle, that there is a concept of energy conservation.